This is a test. Is this working? Yeah. Seems to be working, kind of. Not so much. Okay. Okay, thank you, Francesco. So, welcome to a new lecture of the data management and the visualization course. And today we finish some queries about the last exercise, okay, data warehousing exercise. So we conclude that. I will pick two queries, two extended SQL queries you have in the text here, okay, these two queries here. So we finish two full exercises, the previous with the tickets and the second with the wines, okay? And then we start the second part of the course, which is NoSQL, okay? So later we'll do some back to theory part. So if you're in the Zoom meeting, can you confirm that you can hear my voice and see the screen share with the exercise? Francesco, you said yes. I hope that was the feedback. Okay, because I have no feedback from Zoom in the mic. So that's okay. Thank you all. Great. Okay. So where were we? We were doing this exercise, which is an exercise where we modeled the export of wines, okay, from Italy to abroad, okay? We can read, instead of the specifications, we can read the solution we proposed. And the solution, we see that we have an export country. So we are moving some kind of items outside towards a country. We are moving the items from a given province, okay? Province, region, and area, that is our case. We are moving types of wines. Okay, so now I'm back with no voice, I know, because the mic was off due to the battery. So now we are moving types of wines. We have some kind of orders. We model the orders in large, medium, and small. That's order size, okay? And we have the time dimension, this monthly dimension. Okay, so what's the meaning of this fact table? It contains a row for each group of orders of wines of the same type, okay, with the same order size, okay, in the same month, towards the same country, from the same province in Italy, okay, and with the same packaging. Okay, so I'm moving bottles of 1 liter of the type of wine Barolo with orders that are large from Piedmont to Germany. Okay, that's an example of one row in October. Okay, that's an example of a row of the data warehouse. Okay, you can get this by looking at the logical design. That is the logical design we did. Okay. So you see the province ID, the packaging ID, the type of wine, the order size, the month, and the country. These are the primary keys, okay? So you cannot have duplicate rows with the same values of those keys, okay? Of course, in the original database, you will have for sure, often, probably, many rows with those same values, okay? And the goal of the data warehouse is to collect them all and write here the total of the income of all those rows and the total number of liters you got for all of them. Okay? That's the goal. Now, regarding the queries we are asked to do here, okay, one more thing here. You see you have two different geographical dimensions here. The wines go from one province to one country. Okay, so the province is in Italy and the country is abroad. There are some other exercises. We'll probably do that towards the end of the course from past exams, whose case in the geographical dimension is the following. Okay, you have again. I think the example is right on the sending parcels. Okay, from one place to another. Another example is phone calls. Okay, the phone calls example is in the slides, if I remember correctly. So you are sending something, a parcel, okay, from one place to another. Okay, so if you're looking to the dimensions, you can have sending from, okay, sending from, and then you have the city, and then you have the province, and then you have the region, and all the rest. Okay, and you might have the country, and so on. Okay, and that's sending from. Okay, then you might have sending to. Okay, sending to, and then you have the city, and then the province, and then the region, and then the country. Okay, so here you can write something like parcels. Okay, sending parcels. You can have not total number of items. You can have the weight. Okay, so in kilograms, and so on. The value in euros and everything. Okay, this is just an idea. What happens that in our current exercise, I'm sending from Italian places to places abroad. So the two dimensions are two different information. Okay, are two different values. Okay, one value is Piedmont or Lombardia or any other Tuscany or any other region in Italy, and the other values are Germany, France, and US, and anything. Okay, so there is no doubt that these two dimensions here, the export country and the province, region, and area, are different. They are different also in the hierarchy, because I have province, region, and I have province, region, and area in one case, and country and continent in the other case. Okay, but even if they were the same, so province, region, and area, so I have Italian province, Italian region, Italian area, and a broad province, a broad region. Okay, that will be very similar to the example I'm doing now, which is this one. Where is it? Okay, it's there. Okay, this parcels case. Okay, where I have, well, I have the city, but you can keep only the province or the region. Okay, it's not a matter of being the city or province or the region, but I have a sending from and a sending to. Okay, now if you have different dimensions, okay, sharing some data. So in this case, the parcels, like the phone calls, okay, you might have the same city both in the sending from and in the sending to dimensions. You might have the same province both in the sending from and in the sending to. You might have the same region, the same country. Of course, if you have the same cities, then you have, of course, the same provinces, regions, and countries. Okay, because the province, region, and country are a functional dependency of the city. Okay. So another example could be, I don't know, the phone calls or the emails sent among the students at Polytechnic. You know, you have the emails, the messages, okay, MSG, the messages, and you have from, and you have the student ID, and then you have, I don't know, the age, and you might have, you know, the nationality and other stuff. Okay, that's from. And then you might have to, so the destination of the message, the student ID, the age, the nationality, okay, and so on. Okay, so this is messages. Okay, it's like phone calls. I'm just generating new examples of stuff of events for the fact table which happen between two elements of the same type. Okay, two people, two cities, okay, two phone numbers for telephone calls, okay? In this case, the question is, do we need two different dimensions or not? Okay, and this question raised from the fact that you have the same values here. So if you keep two different dimensions, you end up having something like in the logical design, in the fact table, you have something like from, city, ID, okay, and then to city ID. And then, of course, you will have the city name, the province, and the region, and the same here. Okay, so that's the primary key. Okay, and this is the table schema. Okay, and these two tables will be exactly the same as content. Okay, because if it is very sparse a situation, you will not have the same cities. But after a while, when you are sending all your parcels across the world, you end up having a very large intersection between the two tables. And so that's a waste of space, okay? There is no reason to have two different tables with the same data, okay? So one thing I notice it's difficult to understand is that if you model it like this, in the fact table, so that's, I don't know, cities 1 and cities 2. Cities, yeah, cities 2, and that's cities 1. Okay, so I have two tables, cities 1 and city 2. You can call it sending from and sending to, okay, if you prefer. So yeah, that will be better because I call them sending from and sending to. So let's call the same name. It's better to understand. So that's sending from, and that's sending to. Okay, the two tables. In the fact table, I have parcels, and I have from city ID, then I have to city ID, and then I have the measures like number of items or the weight. Okay, that's our fact table. And this is generally understandable because you follow the pattern. Okay, you have two dimensions, you put the ID of those two dimensions, and it works. Okay, so what's the problem with this solution? It works, okay, but you have duplicate data. I would say uselessly. Okay, and that is the same for the messages here. I have a student ID from, student ID to. If on average I have an exchange of messages among students, I have more or less the same data. So the intersection of the two tables is very large. Okay, that's duplicate data, useless duplicate data. Okay, so how can I solve the issue? The issue is to remove data duplication and to use one table only. Okay, so if I use one table only, what happens is that, let's write it in red here. I have only one table. Let's write it here. Okay, like this. These two tables become only one table. Let's say sending. We can call it sending alone. Okay, sending. I have a city ID, and then I have the city, the province, and all the rest. Please. Now the color, you cannot see that. Oh my God, that's no, it's very clear here, but you cannot see that for sure. Let's write again. Okay. So the red is unreadable there. Thank you. So let's use, I don't know, the blue. The blue is fine. No, not really. I think it's a light there, probably. No, we'll try to close the window and see if that works. Is it better? Not really. Well, I use the white, no problem. You understand the meaning of these is I changed that, okay? So here, okay, I use, let's call sending the city ID. And then I have the city, the province, and all the rest, okay? So duplicate data, one table only, okay? Now, what's the problem with the typical student when you have only one table? That you don't know how to connect that to the fact table. Because you say, before I had my two different IDs, now I have only one ID, how can I connect that to the fact table, okay? And this, you can see the slides, is like the following. Okay, so the solution here is the logical design, but the solution is also in the conceptual design, where you remove these, okay, you actually delete one of the dimensions, and you do two connections here, calling from and to. Okay, from and to. Okay, and this design means that the dimension has two meanings. So it has two connections to the fact table. However, it is stored on disk only once. Okay. Of course, when I do the join, I can join it as the from table or the to table. So as a destination or as a sender of the parcel. Okay. And this translates into having here the same names from CDID and to CDID, and they will join the same CDID here. Okay? So when I do the join in the SQL query, I join the CDID in yellow from the sending table, so this CDID here, with either the from CDID or the to CDID or both, that depends. I generate two instances of the table, and then I can query my data as if I had two tables, okay? So let's write a query just for the sake of understanding this trick, which is not a trick, just a solution. But I can have something like select something or everything, we don't care about what, from, then I can have sending S1, sending S2, and then I can have parcels, which is the fact table P. And then in the where clause, I do the join and I write S1 dot CDID equals P, which is the fact table, dot from CDID. And S2 dot CDID equals P2 CDID. So with this fact that I use the from and the to from the parcels, I'm linking what? S1 to be the from. So S1 is the, I would say, sending city, okay? Sending city, the sender city, okay? And instead, here I have S2 is the recipient city. Okay, and I can understand that thanks to the join. Okay, and then I can set conditions like the from CD must be and you choose the name. Okay, actually not the name, because if you want to work on the name, you must set the name on the cd. And so here you can write something like and s1.cd equals Turin, and s2.cd equals, you choose Paris or whatever you want. Okay, and so since S1 is the sender, when I set Turin, it's from Turin. Okay, from Turin. And since S2, I don't know which color I can use, but let's use the white anyway. To Paris. Okay. So that is how you can use a single table shared among different dimensions with the correct meaning. The meaning is given by the join you write. Okay. So that is basically basic SQL, but I've seen many students having issues with these. Please. Yeah. The question is, can we do the same with the time dimension? Yes. Specifically, you said if you have the same granularity. Okay. So yes, you can do that. One thing that is important is that you have a very similar structure, because sometimes you have monthly data for the purchase, and then you have the date, the specific date for the event. Okay. So if you have different granularities, you can still share the portion of the hierarchy which is shared, which is the same, but that implies an additional join. So you need to split in a snowflake schema the dimension. So just to give you an idea, if you have something like, let's make it like this, you have date, month, year, and then you have something like month and year. Okay, so you would like to share these two. Okay, that's myself in a few minutes, like, okay, a few seconds there. Okay, you want to share these two, you can do that, but that's often not efficient, because you need to introduce a join. So you translate that into something like, let's write it here. You have a date ID and a month ID, and then you have the other measures. So that's kind of example. And here you have number of items. Okay. So here I have number of items. And so date ID and month ID, that's the default. Okay. Then, so that's a fact table. Example, fact table. Now, if you want to take advantage of the shared part here, okay, you need to create a table which contains month and year. And so you must have something like month ID, month and year. Okay. And then the date dimension would be something like date ID, date, and then month ID. And this date ID is the primary key, and the month ID points there. And so when you work with the, let's highlight with, I don't know which color, let's find the green one. Okay, the green. So I work with on the green information. Yeah, you can see that. The problem is that if I want to filter by the green month, okay, or the green year, green means, you know, the one in the upper part, you need to do a join on dimension and then do the filtering. So that implies in an inefficient operation, whereas the month and the year are low cardinality. So the waste in disk space is limited. On the contrary, in this case, the waste in disk space is the full dimension, okay, so 2 dimensions, and it's also useless. So you have no improvement in performance in having 2 different tables. Absolutely. So there is no, it's like a lose-lose condition, okay? Instead here, it's something you need to discuss because you say, okay, I have a small saving in space, but I have a cost in join. So you would tend to waste a little of space for that reason, okay? But in case you are, no, instead of having date, month, and year, you have, I don't know, the millisecond, a timestamp, or the seconds, which are large, so you have many, many numbers. In that case, you might consider that. Another thing, in data warehousing, a pattern for handling the time dimension is the following. You might have a time dimension which is conceptually the following. Timestamp, so that is in seconds. You know, timestamp in computer science is the number of seconds that passed since the epoch. The epoch is January the 1st, 1970. Okay? And so a timestamp is the number of seconds since the epoch. Okay? That's a computer science definition. Okay? So timestamp is very much used in computer systems. Okay? And so you might use this reference for storing some events that happens in the word. Okay? So the timestamp is seconds, basically. So you can group the timestamp, okay, in minutes, in hours, in days. So this is a date. And then in months and everything. Okay? This is conceptually correct. However, it's violating one of the key points in data warehousing. That is, the dimension cannot be huge. Okay? So, you know how many seconds has passed since the epoch so far? It's millions. Okay? So if you have one value for each second since the 70s, this dimension is millions, okay, of records. And that doesn't make any sense in data warehousing, okay? So how can you solve this problem? You solve it by splitting the dimension. And so instead of having the seconds themselves like these, you split these typically at this point, okay? So you have the first portion describing all the seconds in a day, okay? So you go from how many seconds in a day? It's 24 days, 24 hours for 60 minutes for 60 seconds, okay? That's, okay? So that's number of seconds in a day, okay? Which is a large number, but that's manageable, okay? And so that's the dimension modeling all the seconds in a day. And that's a dimension. It's finished. Then you combine that dimension with the dates. Okay, so this becomes this value. Okay, so 24 hours for 60 minutes for 60 seconds. Okay, so that's 80K different values, which is quite a large value, by the way. And then the days, instead of being connected here, are connected directly to the fact table. So you start again from date, month, and all the rest. okay? And so here, instead of the pure timestamp, you actually have not a pure timestamp, but a value from 0 to 80,000 or 80,000 something. We have seen that it's 86,000, okay? And so that is another pattern which actually breaks the pure conceptual idea of functional dependency, because if you use the timestamp as it is, so the second since the epoch, you can actually have a functional dependency between the timestamp and the date, okay? Because each timestamp belongs only to one date, okay? And vice versa, a date groups all the timestamps of that day, okay? So even if you have a functional dependency, that is not enough to model the hierarchy, because the hierarchy must also be efficient and sustainable. And it would not be sustainable and efficient if you connect all those values, okay? So imagine these are the values for one day. And so how many days has passed since the 70s, okay? And you can multiply the value, you get millions, okay? Okay, so that is a pattern. In case it happens to your real life or an exam, an exercise, you need to model something below the date. So the hours, well, the hours, it's kind of borderline, because the hours multiply the dates by 24 only. So sometimes if you only have the hours, you can actually keep them connected to the date. But if you go below, like the minutes or the seconds, you tend to split the dimension, even if you have a functional dependency. And so you model the seconds, minutes, and hours as a separate dimension, okay, which repeats every day, okay? So at this moment, you see it's here, it's 50 seconds, 48 minutes, sorry, 58 minutes and 13 hours since the beginning of the day, okay? So that's the value I would get for this dimension at the moment. Then in a separate dimension, I have today is October 28th, okay, in a separate dimension. In this way, I have a manageable dimension, two manageable dimensions, okay, and I can survive to the inefficiency, okay, breaking conceptually the functional dependency, okay, but the final goal, so the functional dependency purpose is not to force a theory on the practice. It's just to help the practice, okay? Help the solution to be efficient and to model the reality you're modeling, okay? So that's another thing I want to mention about this exercise, okay? So we're talking about, this is a focus on time dimensions below the date, okay? So if you go into details like seconds and minutes, you split dimension, okay? You split here, typically, okay? So the day and so on goes to another side. Instead, if you have two dimensions which are the same, you can share them. In this case, the shared portion is small and makes the solution inefficient. So you wouldn't share these two portions. That's useless. We are talking about small amount of data because, you know, the number of months, imagine you have, I don't know, 50 years of data, okay? It means in the end, you have kind of 1,000 months. So it's very small amount. You can have it duplicated instead of having a join, okay? Instead, when you have kind of large dimensions, like here, you have all the cities in the world, okay? In that case, you have to share the dimensions. So it's absolutely useless and there is no advantage in keeping the two separate, okay? If they come from the same domain, so all the from cities can be two cities and all the two cities can be from cities potentially, okay? Because instead, if I'm only, I don't know, managing exports of wines from Italy to abroad, again, we fall back in our exercise case where we didn't share the dimensions, okay, besides being on different hierarchies, okay? So this is the case when the two dimensions share the same data, the same cities. Then you design with these sharing. So this is the portion to share, okay, the from to on the lowest attribute. And you design it like this, okay? So the red solution here. So no duplicate tables, one single table, and then you manage the meaning of that table being from or to, sending or recipient, sender or recipient, in the join, okay? So this is the case. So fixing Turing on S1, S1 is the from city, you see from the join. So I'm selecting all the records, sending something from Turing. And the same reasoning for Paris, okay? And the trick is I generated two instances of the sending table, the table with the cities, S1 and S2. Okay, so this is basic SQL, but sometimes we forget about it. And so no extended SQL, but just basic one. Okay, fine. So these are two patterns. Thank you for the question, because this was another interesting pattern I wanted to mention, but I was forgetting. Two patterns you can use in the warehouse design. Okay, was that clear? Okay, please. Yeah, so we have another question. The question is, how did we manage the order size table? So we are here, okay? So the question is why order size is here and we have no table regarding order size, okay? So we can write it here, order size, I know this country with an N, okay? So order size, that would be the other option. So let's make the other option. We have order size ID and then order size. Okay, something like this. And order size ID would be the primary key. So that would be the basic options. The default, okay? If you solve it mechanically, you would create an order size because why? Why? Because we are here. Okay, we have order size at dimension. Every dimension becomes a table with a surrogate key. So mechanically, this is the way to go. Okay, mechanically, I would create this order size table for sure. Okay, now what's the reasoning behind it? If I create such an order size table for 3 records, because that order size table will consist of 3 records, order size ID 0 will contain order size small. Order size ID 1 will contain order size medium, and then order size D2. Okay, let's write it that here. Let's copy these so it's faster. Let's write it here. And I need to do these. Okay, great. All the size. Okay, so this is the table. Order size 0, that's small. Order size 1, that's medium. And order size 2, that's large. Okay. Large. Okay. That is our order size table. Okay. So what's the reasoning about our option to push down the order size is the following. If I write actually in the fact table, so here in the fact table, I write these values, that's not a good idea. Because these values are strings, okay, and strings consume many bytes. Okay, if it's Unicode, I think it's 4 bytes each character, and so this becomes, and then the varchar also must have a kind of size of itself. So you consume like tens of bytes for each value. Okay, tens of bytes for each value. Okay, multiplied in the fact table by billions of records. Okay, so tens of bytes by billions means tens of billions of bytes. Okay, so gigabytes wasted for nothing. Okay, for just storing something repeatable. Okay, that is the reason why we use the order size ID, which is a surrogate key, which in say 1 byte or even less, but less than 1 byte is difficult. Okay, actually in 2-bit, it's enough to store that data. Let's say 1 byte. Okay, and that would save a lot of space in the fact table. But we can do a better option, which is saving the join. So if I model the order size here directly as 012 or 012, yeah, 012, I can directly store 012 saying 0 is small, 1 is medium, and 2 is large, and I just put that into documentation, and everybody is storing that information, is knowing that information in the query, okay? And I can do that because it's easy, understandable, small, manageable, okay? So it's a matter of practice, not a matter of theory, actually. It's a matter of practice. That's the reason why we do the push down, okay? If you had complex choices, many values, some kind of increasing values over time, or categories that can be expanded, that wouldn't be a good choice, okay? Yeah, for the packaging, we discussed that, but for the packaging, our hypothesis was that the packaging of the wines is kind of complex because you have different type of bottles of different size. You have bigger than bottles container in glass. You have container in like in the Tetra Pak. Okay, so many options. So that would be less feasible because otherwise the packaging ID 72, what is it? I don't know. Instead, order size 012, it's easy. Okay, that's the point. But in any case, when you can push down a small value in the fact table, that's a good choice. When you need to push down a complex string, imagine the packaging string, which might be a bottle of 1.5 liters in glass with, I don't know, some signing or, anything, okay? That is a very long string. You cannot repeat that in the fact table billions of times. Okay, so that's unfeasible. So that's the reason why we use dimensions. Okay, great. Thank you for the question. Other questions regarding this exercise? No questions? Okay, great. So let's focus on the queries now. So here we are. Considering only wines that have DOC certification exported to Asia, select the average price per liter for each year. So this is first metric, okay? Average price per liter for each year. The percentage of liters exported in the year compared to the total for all years, okay? So that's percentage of liters, okay? And then cumulative yearly total of liters exported, okay? Performing the analysis means all the measures separately for each type of packaging, okay? So what I should notice here is the following. I have for each year, in the year, all the years, yearly total, okay? So I would suggest to start with something like, let's see if I can make you read both. Yeah, okay. I should, okay, I'm just taking this and putting below so we have space for discussing about this. Okay. Like this. Okay, great. So here I have something, in the query, we need to select something. Okay. That's small, in my opinion. Let's make it larger. Okay. From something. Oh, yeah. From where, group by. And then we might also have order by and other stuff, okay? And also having and all the rest, okay? So in this case, I need to identify first the group by. Okay, the group by is driving our query. So I have performed the analysis separately for each type of packaging. So no doubt that everything must be separate for each type of packaging. Okay. So in the end, I will have something which is type of packaging here, and then some values. Okay. Then I have three measures. All the three measures are for each year, yearly, for all the years. So again, the doubt must arise. Is it a yearly separation, even if it is not stated separately by each year and each type of packaging? Because what I want here is select the average price per liter for each year, the first metric. So this means that I have something like the year and average price per liter. Okay, because in this case, I want, well, for each packaging, we don't care about the packaging, something, year 2023, that's the value. And then year 2022, that's the value, and so on. Okay, so that is what I want as a result. And this means that I must need the year as a on each row. Okay. And the same for the percentage of liters exported in the year compared to the total for all years. So the percentage means this year, how much this year contributed to the overall total. Okay. So on all my history, I exported 1 million liters. How much this year contributed to that? Okay. And so again, I can change the name of this column, give the name of percentage, and that will be the same. So it would be, 2% this year, 1% last year, and so on. Okay. Depends on how many years I have. Okay. And then the cumulative yearly total of liters exported. This means since the beginning of my company of exporting, how many liters do I have exported so far? And I want to sample that every year. So 3 years ago, I was at 1 million. Then 2 years ago, I was at 2 million. Then this year, I am at 3 million, and so on. Okay, so it's like the cumulative number of credits of exam passed by each student. Okay, every year, or every month, or every session. Okay, so that's the idea. So if I want this behavior, I want for sure the type of packaging. So let's call it pack type to make it short, and year. That is what I want. And then I have all the other metrics. So I have metric 1, which I will do, metric 2, and metric 3. Okay, in the select clause. And so here in the group by, if I want to divide my numbers by packaging type and year, I must group by packaging type and year. Otherwise, I cannot access those values, those attributes. Okay, so that's pack type and year. Okay. Now, let's try with this schema, this structure, to answer, for instance, the first query. The average price per liter for each year. So if I write these, I have access to what? I have access to information of total income. Let's see the fact table, which is here. Okay. I have the total income, which is the price, the overall, the sum of all the prices of all the wines sold in that province, region, order, month, and so on, and the total number of liters. So if I divide the two, I get the average price, okay? Because I have the total number of liters and the total number of euros I got, which correspond to the price of those liters when I've sold them, okay? So here the metric is quite simple because I'm basically only doing the average price per liters, means the sum of the price, we call it income, divided by the sum of the liters. Okay. What's the warning here? The warning is average. Okay, average, no income or average liters or anything else. Okay, you might think of. Okay, let's put it in. No, you cannot see the red. Yeah, you can see the red now. Okay. Okay, average income or average liters or average of something. What's the problem with the average of something in SQL? Is that the average in SQL is the sum of the metric, like the sum of the income in this case, divided by the number of rows. And the number of rows is not the number of liters, of course. Okay, of course. So you can do average income like in red only if the design of your data warehouse guarantees that you have one row for each liter of wine sold. That is not the case of our data warehouse. Okay? So sometimes the AVG function is correct when you are dividing by the number of rows, and number of rows as a semantic which helps in your metric, in your measure, mathematically works. Okay? But 99% of the times doesn't work. Okay? And even if it works, it's better, and in my opinion, more explicative, more self-understandable to use the sum divided by the sum. Okay? Okay, so why not average income? Because it would be sum of income divided by count. Okay, that is the reason why average income doesn't work. Okay, I like to make it like this. Okay, so this is no, because, okay. So average price per liter for each year, that's the case. So this is already for each year and for each packaging type because it's computed on the group by. Okay, so I have one value for each year and for each packaging type, automatically done by the SQL, which does the for loops and selects data and does the computation. Okay, so this is basic SQL, by the way, no extended SQL. Then we have the second metric, which is the percentage of liters. So when I see the percentage, I say 100% multiplied by something, okay, of liters exported in the year. Let's stop here. How many liters do I exported, or did they exported in each year? Okay, if the query were how many liters were exported in each year, that would be simple because I have this table. Okay, in each year, okay, I want the number of liters. I have a column called number of liters. I just sum for each year. So that would be very easily the sum. Oops, I'm writing the wrong place. Okay, the sum of the liters. This is the amount of liters sold in each year. And so that is exactly this first part of the query, liters exported in the year, in the current year. Okay, so I need to compare this value which is the yearly value, with respect to the total for all the years. Okay, so I need to compute a second comparison. So the percentage of this year with respect to all the years. Okay, so I need to write for sure a sum of sum. Why? Because the inner sum, let's highlight this in some kind of color. Let's use the can you see the yeah, kind of, okay. So this and this, like this. So the green sum of leaders always work on the group by. So that's always the yearly amount. Then the second sum sums the yearly amounts. So the second sum sums those. So let's write here the sum. Okay. The sum. Oh, I have it in the history. Yeah, that one. Okay. Sum of leaders. Okay. So that's the sum. Okay. So the second sum works on top of these. Okay. It's the sum of all the sums. Okay. Over what? Over a partition. When do I stop summing the years? I stop summing the years in this query, which is a query where I group by packaging type and year, when I change packaging type. Okay, so I want us to understand for each packaging type how much his year is contributing to the overall of all the years. Okay, and so I partition by, which means I reset the counter when I change packaging type. Okay. Okay, so that's how the second sum works. The second sum sums all the years. When I change the packaging type, I reset the counting. Okay. If you want to have an example, here you have packaging type 1, and then you can have a packaging type 2, 2023, and packaging 2, 2022, okay, and so on. So here you are summing what? You are summing all these and all these separately, because this is the partition. Okay. Partition. Okay. Can you see the blue? A little. Let's do it with these. Okay, that's the partition. That's better. Please. Yeah, we can do that. Yeah. We'll see in a minute. Yeah, thank you for the question. Only wines that have DOC certification exported to Asia. So we need also to fix these. Generally, that's the last problem because it's very easy. You set in where clause the conditions. Okay, so in the where clause, when we arrive here, we'll set DOC and Asia. Okay. Thank you. Will remember me when we arrive there. Please. No, the question is, what happens if I don't have the packaging type? Okay. If you don't have a packaging type, what happens is what you find in the slides, there is a partition over with no attributes. Okay, you cannot write double sum without over. So a double sum implies an over because otherwise you don't know the second sum, the outer sum on what you need to compute that. And so you need to write over and then it's empty. You have no partition. So it means the whole table. Okay? It's in the slides anyway. You have an example in the theory slides. Okay, thank you for the question. Other questions? Yeah. Yeah, okay. So the answer is here. Let me see if I can. No, I don't have the slides ready here. If you look at, try here. Probably it's here. You write simply over and that's it. But I'll show you. I'll show you because we have it here. We have it here. It's I think this one. Let's see if I can find the example quickly. Yeah, I think it's here. I think it's almost there. Must be either in these or in the over partition by CD. Yeah, that one. This is the example. You see? You have over without anything. That's the answer to you and to you. Okay? You have no partition. It means the whole table. Okay? And that would happen if you hadn't the packaging type. Okay? Great. Okay? So that's what happens here for the second type. Let's finish with the third. And the cumulative yearly total of liters exported. That's a cumulative. Okay, so this means that a cumulative works like this. I'm summing years. Okay, so let's do it in example. If I copy this table, I put it here. I can write something like, well, I can use this actually, but I need some other years. So let's say 2020, 2021, 2022, and 2023. And that is the same packaging type. Okay. Then I change packaging type. I start again, and I continue like this. Okay. 2021, and so on. Okay. So what happens is that, again, it's separate for each packaging type. Okay. That's a partition. And then I do the cumulative. So I sum these two in these here, these three in these here, these four in this here. That's a cumulative pattern. Okay. And so what I need to do is the sum of the sum over, okay, the sum of the sum over, okay, over what? I have the same partition, okay, because when I change the packaging type, I reset the counting. I order by, okay, you know, order by year in this case, because I'm summing the years, you see, cumulative yearly total of liters exported. Okay, I can order the year. Rows unbounded preceding. Rows unbounded preceding. So that's preceding. That's the cumulative pattern. Okay, so let's put it more clear like this, and like this. Okay, so that's the cumulative pattern. Then you have the from clause. You surely the fact table. How did we call the fact table? Don't remember. It's called wines. Okay, so I have wines from wines W, wines, okay, W. Then I have, what other tables do I need? I need the packaging type and the time dimension. So the packaging type is here, packaging type, and but actually packaging type has no filters, so I don't need any filter on that. The time dimension is the month ID. Okay, so I need the month ID definitely. It's called, how is it called? The time dimension, it's called time. Okay, so from time dimension T, then I have to select on the certification and the export country or export continent. So I need the certification, which is in the wine type. Okay, so I have one type and country. Okay, that's the export country. So here I have, okay, I can delete that. Okay. Okay. I need the export country, so it's country, that's for Asia, C, and the wine type for the certification. Let's say WT. Okay. Now, how can I can fix the filters? The certification doc. Okay, so from the wine type dot doc, this must be, let's say, true. Okay. And country, no, country dot continent must be equal to Asia. Okay. That is how I filter that. Okay. Notice that if I change slightly the query, not only wines that have DOC certification, but wines that have only the DOC certification. Okay. So if I change this query and I say wines that have only the DOC certification, okay. Thanks to the configuration pattern we used in modeling the certifications, we are able to answer this query very easily. Okay. How would you translate that to the solution? It's here. So this contains a table like this. We've seen that. Okay. You see, that's the case. How can you filter the wine types having only DOC? You set DOC to 1 or true. I've chosen 2, but it can be 1 or true or any Boolean you like. And you set all the others to 0. Okay. So it's easy. Okay, straightforward. Instead, if you had used the add option, so the, that one, this option here, that would be a not in clause. So an anti-join operation, which is expensive. Okay. So that is one thing worth mentioning here. Okay. So in case you want to fix that, that would be end wt.docg equals, let's say 0. So let's use 0 and 1. It's easier. It's faster. And wt dot, I don't know, another certification, ddd you like, okay, 0, and so on. Okay. Okay. This is for the purpose of making you notice how easy it is with the configuration pattern to filter your data. Okay, which is not the case for the multiple edge solution with the join of an additional table. Okay. Okay. Besides that, we also need the join conditions. Okay, so we need to join these 1, 2, 3, and 4 tables. So we have the wines W, which is wine ID, I guess. I don't remember the IDs, but let's say it's one ID with the, no, sorry, wines is the fact table. So wines has to join with time. So time ID or month ID, that was month ID. Month ID equals time t dot month ID. Okay. And then you also have end. Then you have w dot country ID equals country dot country ID. And the last one, I have 4 tables, so I must write 3 joins. Okay, it's the number of tables minus 1. That gives you the number of joins required to avoid a Cartesian product. Okay. Wine type, so w dot wine type ID equals wt wine type ID. Okay, so these are the joins. Okay, these are the joins. So this is 4 tables implies 4 minus 1 joins. Okay, like this. Then group by pack type and year, and order by, we don't need any order by, it's not written, but yeah, you can choose an order by if you like. Okay, just to present your data. Okay, is that clear? Questions? No questions? Okay, so we can have a break. Okay, see you in 10 minutes. Thank you. Okay, so let's close this exercise so we can go on with the NoSQL part. First of all, I forgot in the previous solution to include the packaging type table. Why do we need the packaging type table? Because here we have the partition by packaging type, because here we select the packaging type, and because here we group by the packaging type. Okay, so the packaging type must be present. Okay, must be present in the tables. Otherwise, I cannot access this information. Okay, this one, and this one. Okay, so that is the reason why we need the packaging type as well, but I forgot previously, so sorry about it. Let's add the packaging type. This means we have no 4 tables. Okay, we have 5 tables now. And so 5 minus 1 joins. So let's add a join here. So W pack type ID equals P dot pack type ID. Okay, ID. Okay, so the join is very easy. You join the primary key of the fact table with the primary key of the dimension you're joining. And that's always like that. So joins are mechanical, okay? So that should be everything for this query, okay? So let's do also query B, and then we go on with the NoSQL, okay? I'm just copying that below so it's easier to follow. So for each region, select the average price per liter, the average number of liters of wine exported per province, the percentage of liters of wine exported from each region with respect to the total of the geographical area to which the region belongs. Okay? Perform the analysis separately for each year. Okay, so what are the group bys? Let's try to highlight the group bys. I would say for each region, no. That one. For each region and for each year. Okay, these are 2 elements for driving the group by. Let's try to build such a structure. So select. Let's use a larger font. Okay, so probably I have the region and the year. And so at the end in the group by, I will have the region and the year. Okay, let's see if this works. Okay, that's is a tentative solution. Select the average price per liter. Okay, so we are here. The average price per liter. We have already done that. Okay, before. The average price per liter means the sum of the price, the sum of the liters, and that's the ratio. So basically, this is the same as before. Okay, so this is the same as before. So it's sum of the, it's called income in our case, divided by the sum of the liters. Okay, that's always the same. Okay, then we have the average number of liters per province. What's this? This is like I have something like let's draw like this. I have something like, well, where can I stay? Let's stay here. Average number of liters per province. So liters, province, okay? And then I have other attributes. Let's say the month or something like this. Well, the month, no, because we have the year. Yeah, let's put the year, okay? Yeah, we can be the month and the year, okay? So 10 liters, Turin, month 1, 2024, year 2024, okay? Then I have 20 liters in Turin, second month, 2024, oops, and so on, okay? Then I have another value for another province, Cuneo, which is in Piedmont, but we don't care another province. And I have some values here. Okay, so if I continue like this, what happens? I can have other provinces here. Okay, and for each of them, I have many numbers. Okay. What's the average number of liters per province? If here I have 10 plus 20 plus 30 plus 40, okay, this goes to 100 total liters. And I have Turin, Cuneo, and Alessandria, three provinces. What's the average number of liters per province, average amount per province? It's 100 divided by 3. So 3 provinces, 100 liters overall. On average, I have 33.3 liters per province. Okay? Across what? Across my group by. So for each region, for each year, that's what I need to take into account. So in this case, this is one region, Piedmont, all provinces from Piedmont. Then it's 1 year, 2024. Okay? So within the group by, this example, this table is before the group by. Okay? When I execute the group by, I will have here, let's see if I can do that. I have region, okay, that's Piedmont, and so on. Okay, so yeah, like this. I have the same, okay, the same here. Then I will change the year and the region, which are my group by levels. And so I compact all this information for each year and region. Okay, so in the end, I will have something like year, region, average liters per province. And so when I'm 2024 Piedmont, then I have 100 divided by 3. Then I will have the other values. So 2023, 2022, Piedmont, Tuscany, and all the others. Okay? So this is, I don't know, example above group by. Okay? And following table is after group by. Okay? So you have 2 examples. Okay? So how can I compute that in SQL? In SQL, I can do that by writing here average number of liters of wine exported per province. The 100 total liters liters here. Okay, it's the total of the liters. So that's the sum of these values. Okay, so here I simply write sum of liters. Okay, now we need to divide by 3 provinces. How can I do that? Do you have any clue, suggestion? Please? Yeah, he's saying, can we do another select statement and do a count on distinct provinces? Yes, the count of distinct provinces is correct. We don't need another select statement. You can do it in line. Okay, please. He's suggesting count over partition by region. Actually, if you count what asterisk, count star, over partition by region, you are counting how many rows you have for each region. Okay, so that would be, in our example, 1, 2, 3, 4, and also the dots. Okay, so here you count the number of different provinces. So it's distinct provinces, province actually, province. Okay. Okay, so that's the case. So if I count number of distinct values of province here, I see it's 3. Okay, no matter how many duplicates I have of Turin, Cuneo, or Alessandria, we don't care. It's distinct province. Okay, so that is the case. Okay, for this situation here. That's the second metric. It's a percentage. So it's average number of liters per province. So that's okay. So that's the second metric. Then the percentage. Okay, so the percentage of liters of wine exported from each region, and we are already in each region. Okay. With respect to the total of the geographical area to which the region belongs. Okay. So this means that I have to do something like here. Let's do the following. I have the area. Okay. And I add the region total. And then I have the area total. And so that's the area, let's say north. Okay. The region total is a given number, and the area total is another number. I want to do the ratio. So when I go on, I have, let's say, the same here, another region. Okay, which has a different number. And this is the same, because the area is always north. Okay, and I need to compute this percentage. Okay, when I sum all the regions in the north area, I get 100%. And I do the same for the center area, the south area, and for each year, 2024, 2023, and so on. Okay, so that is what I need to do. How can I do that? First, the percentage of the amount of liters of wine exported from each region, okay, is already the one I sum here. That is the amount exported for each region, okay, and for each year. Of course, that's a group by level, okay. So that is what I need to put into the ratio, and then I need to compute the same value, but for not the region, but the area. So I need to sum all the regions. So my partition, when I stop counting, when I reset the counter, is the area, okay? So that I'm summing all the regions in that area. And so how can I do that? I will have the sum of liters, which is summed again, because the sum of liters is the region amount. I want the area amount over, okay? And then here I have a partition by area, of course, Okay. And in this way, I'm resetting the counter every time I change the area. So I'm summing all the regions belonging to that area. So Piedmont, Lombardia, and so on in the north. Tuscany and Lazio and everything in the center. Sicily and Puglia and everything in the south. Okay. However, I must also stop when I change the year. Okay, because if I don't set the year, so I don't have this. If I don't have this, okay, it means that I sum all the regions of an area for all the years. So they will be uncomparable, because instead, what I'm computing at this point, okay, is the yearly region total, because the group by is region and year. Okay, and so if I don't compute that yearly, doesn't make any sense. Okay, and so for this reason, at this point, I need to select also the year. Okay, so that's correct. Like this and like this. Oops. Okay. And that's our case. Okay. North, central, and south. Okay. That's all. That's all. We need that all the metrics are finished. Now we need also to do the from clause, the where clause, and the group by. Okay. So the from are the tables and the where are the joins. We have no filtering of any other kind. Okay. So I will leave that to you. Okay. And also query number C. I will leave that to you. It's only a ranking, I guess. Okay. So did you follow that? Is that clear? So here, the most common errors I see is forgetting this one. Okay, that's a very common error. And making strange things to compute this one. Okay, these are the two most common errors I see in this kind of queries in the exam. Okay, so let's focus on these issues and see that you got them. Okay. Otherwise, please ask or come to lab practice for asking. That's all welcome, or use Piazza and we are available. Okay. So that's all for now. Then we'll try to find some time at the end of the course to practice with some past exams. But basically, these exercises are already taken from past exams. Okay. So you should expect slightly harder exercises, but that's the goal. Please. Yeah, thank you. That's a very common error. Thank you. Thank you. Yeah. Area, you see, area is here, okay? But it's not in the group by. So you cannot execute this query without putting the group by area as well. Thank you. That's very common. Yeah. So that's a mechanical check you do at the end of the query, okay? For sure, okay? Because otherwise, in the partition by, you cannot see the area. Okay. If you add the area, nothing changes for the group by, because the region is more detailed than the area. And so adding the area doesn't change anything in the group by. Okay. Besides adding the area field. Okay. Thank you. Yeah. Okay. Other suggestions? Or, yeah, please. No, area is compulsory. Area is compulsory. Okay. Compulsory. In the group by. And of course, also in yeah, it's compulsory everywhere. Also in the group by, let's say, also in the group by. Yeah. Oh, it was my fault. I forgot, but it's to be added absolutely. Okay. Other questions? Okay, no questions. Great. So we close here with the data warehousing part. Please do practice. You have a lot of exercises. I will publish draft solutions for the exercises. I'm asking Simone to publish also the latest exams from 2024. Okay, so you don't have to pay your colleagues to get them. I'm for free knowledge. Okay, so we'll publish all the past exams on the website for sure. So you have access to a lot of exercises. Okay, to a lot of exercises. If you have questions, please ask on Piazza or come to the lab practice. Okay, that's the best way to get assistance. Please. Yes, you want me to also export the PDF of my notes, right? So this OneNote stuff. Okay, I don't know how nice it will be because I know that exporting in PDF from OneNote is not very straightforward. I published the screenshots. Yeah, so we'll take screenshots. Yeah, that's the only way in which I can make it reasonable. Yeah, okay, for sure. Okay, we'll publish on Piazza as last time. Okay, please. I can try. I've never done that. We can try. Okay. Okay, great. So here we are. Now let's take the slides and let's start the NoSQL. So here we are. Okay. Let's share the screen for those in the Zoom meeting. Okay. Yeah, later. I would go for the relational because you have a practice on NoSQL in 2 weeks. So I want you to be ready for the practice on NoSQL. And then since the physical structures are kind of an add-on, okay, we can do it later without problems, okay? So no relational databases. So that's the second big topic of the course. And it tries to challenge everything we know about relational databases and about relational data. So the idea is everybody's used to use a table for managing data, okay? From Excel to any other form of data management system, the table is everywhere. Tables are everywhere. And that's nice, okay? There are some cases when these assumptions do not hold anymore, okay? I will try to briefly at the beginning recap some key features of the relational word, okay? Because you see this topic is something strange, non-something, okay? It's kind of against something, okay? Sounds like against something. Sometimes it's called also NoSQL. We'll see that in a few slides, NoSQL, okay? So I'm against SQL. I'm against relational databases. Why? Is really against or not? So it's a kind of tricky topic because to understand how this was born, we need to understand why relational databases are so popular, so useful, so fine, so okay, so good. Okay. So a brief recap here. You might know some of this stuff, but we need to focus on a few key features. First, oh, what's this? I don't like this bar here. Okay. So first, data management is based on many technologies. Okay, we have many options. The slide will be 10 slides that long. Okay, just a few keywords. Data warehousing, we know. Now we know. NoSQL databases, we will know in a few hours. Okay, MapReduce, we see a little about this in this course, but you will have a specific big data course on MapReduce. Okay. Then you have how to store distributed data in a cluster, okay? So HDFS, you will study that in big data course, okay? Together with MapReduce. Then you have even more. You have grid computing, you have cloud computing, okay, you have HPC computing, you have big data paradigms, you have large scale machine learning. So you have a lot of technologies about managing data and harnessing like modeling, predictive modeling, recognizing images, text, okay? So you have a lot of information about data management at large, okay? So now we focus specifically on these portions. I will give you some brief examples of these, okay? And I will just touch a little of this probably, okay? So we just focus a small portion of everything we should know about these topics. How were relational databases born? They were born a long time ago. We are talking about the 60s, the 70s, okay? And they became the predominant, they are still the predominant, okay? They are still the predominant solutions for managing data. Before them, there were some kind of hierarchical modeling or other stuff we don't even remember, okay? So much relational databases were successful, okay? And the basics behind that, so the basic principles of organizing data in relational databases are the things you know, but we need to focus on because we'll challenge that, okay? First, we have the tables, okay? How is a table made? A table is made by having a row, okay, and a column, a row set and a column set, okay? So all the rows are of the same type. This means that you have, you know, a schema, it's called. So this portion here is also called the schema, okay, which tells us how the table is made of, how each row is made of. So if I have a table in Excel, let's say Excel, it's fine, okay, it's not a database, but it's fine. I write student name, student surname, student ID, then I insert the data. I automatically expect all the rows to have a name, a surname, and an ID. That's so automatic, so standard that everybody expects that, okay? And that's fine, and that's fine. This is called schema. I have a bunch of rows, and all the rows share that schema, okay? If I want to add something to any student, I need to add the new column here, and I add the column for all the students. Even if then I insert the value only for some of them, but I need to add the column to all the students, all the rows, okay? Each row has a primary key. The primary key is a special attribute whose purpose is to identify uniquely each record, each row. It has the two features, unique and not null. So it must be evaluated to a given number, to a given value, being a string or a number, we don't care. And it cannot be null, and it must be unique. So no two rows exist having the same primary key, okay? We create many tables in general, the students, the exams, the teachers, the universities, and the degrees, and everything. And then we join the tables. So we use something called foreign keys, okay? We can also use other attributes actually in general, but we tend to use foreign keys with primary keys, okay, to join different tables. Okay, so if I have passed an exam, my table would be something like this, okay? Not passing exam, this is the example for enrolled in, okay? So some students are enrolled in some courses, okay? So how can I model this information that students are enrolled in a course? I cannot insert a list of students inside the table of the students, sorry, or the course, or insert a list of courses inside the student table. In relational databases, I use a supporting table, okay, which is this table here, the takes course. Okay, so how can we read that? I think most of you are able to read this table, this example. given a course like this course here, I can look for all those having this course. Okay, let's take 1002, which has 2 samples. And so I know that the number of students enrolled in that course is 2, and the 2 students are this one. Okay, actually we have the same student here because I have different semesters. Okay, but apart from that issue, I can fix a semester and count number of students. Okay, so with this supporting structure, I can answer all the queries. How many students for each semester, how many students in each course, how many courses each student in which semester, and so on. Okay, I simply do the join operation, which matches primary keys and foreign keys, or general attributes of different tables, okay? Matches the values of those attributes and returns me the result, okay? You have also the SQL language here. By the way, the last point was SQL language. So one thing that the relational databases are strong for is a common SQL language. Then we have many dialects, but in general, the core of the SQL is a standard. And if you have a relational database, it understands SQL full stop. Okay. And so that's the case. Okay. That is how things work. So how can you build a relational database system? First, smallest units. Why? Because we need to normalize data. So it doesn't happen that here in the course table, I have students and then I have the list. Okay, so something like this. Okay, doesn't happen. So it never happened this, that I have a list of students inside the course table, because I use the join with the students in the supporting table. Okay, and that generates a new table having one row for each couple course and student. Then I group by, I count, and I get the result I want. Okay, but if the students are in this table, I cannot use any information of the students here. Let's say I want the name of the students of the course. I cannot say here student's name. Okay, let's do that just for the purpose of understanding what I mean. Student's name. Okay, and here I can write, this is Matt, if I got it right. This is Jenny, and so on. And then the other one is Sean, I guess. Okay. And all the others, by the way, because I can have many students enrolled. Okay, so I have a list of names. Okay, this never happens. Why this never happens? Because we use normalization. Normalization says that if I have the students here, all the information of the students must stay in that table. And so if I have to fix the name of a student, I change it here, and that is the only place where I find that value. Instead, if I had written Matt also there, my responsibility to find in the whole database all the places where I duplicated the name of the students, and I need to go and fix that. Okay, and this is a problem. Okay, this makes things much complicated. Instead, normalizing data, so having each value, apart from foreign keys, each value, each information, like the name of the students, date of birth, and the nationality and all the stuff, only in one place makes things much easier. Okay, because if you want to fix something, to change the value, to update the value, anything, you know it's there. It's the only place where it is. Okay. On the contrary, the drawback of this behavior is that whenever you need that information, you pay the cost of a join. Okay, so this is the compromise. Okay, the trade-off. If I had the name here and I want to return on a web page the list of the names of the students for each course, no join. It's already there, the value. It's already in the table I'm reading from. But I pay the cost of updating, propagating updates, and all the stuff. Okay, so this is the advantage of normalization. Okay, this is a pattern in relational databases, which is foundational. Okay, everything in relational databases is normalized. Okay, this is broken partly in data warehousing. Okay, in data warehousing, you break the normalization because you have the star schema. If you had used the snowflake schema, then you would normalize data. But that would cost you the join operation, and the join is expensive, computationally expensive. For this reason, we have this trade-off of using a star schema with the limited amount of joins only between the fact table and dimensions, but the dimensions are denormalized in data warehousing. Okay? The schema is rigid, which means all the rows have the same attributes in the same table. Okay? So here, if I ask you the class ID 1004, which is the new one here, which attributes does it have? It has a class ID, a title, and a class number, for sure. No doubts. Okay? That's a rigid schema. Can you change that? Yes. Only if you change it for all the rows, for the whole table. Okay? Queries merge data from different tables. Yes, that's called join. Write operations are simple. Why? Because you know the schema. So you know that you need to write those information in those places. Okay, no options. Search can be slower. Why? Because the join is computationally expensive. Then you have the guarantees for transactional processing. Transactional processing means that you follow the ACID properties. I don't know if you have heard about ACID properties. We'll talk about that later. So I just tell you what this means. If you move some money from your bank account to my bank account, you want the money to be transferred at once. Okay? It cannot happen that half of the money is transferred or it is added to my bank account and not removed from yours. Of course, you would be happy, but the bank is not. Okay? Or the other way around. So I don't get the money and you have lost the money. So it's lost. So the bank is happy, but we are not. Okay? So this is a very brief intuition of the fact that sometimes when you, that's a typical for transactions in financial domains, but it also in other domains, okay? Like purchasing an item on Amazon, okay? If you got it, you want it, okay? It's not that sometimes doesn't happen to work, okay? For many operations, an example, you change the password, okay? If you change the password, you want the new password to work and not the old one, okay? So it must be complete. Not that half of the new password is accepted and half is the old one, okay? Or that both passwords are still valid, okay? Or things like this. That's transactional processing, okay? So let's move towards NoSQL now. What's the goal of relational databases as key features? So where is the value of relational databases? Joins, transactions, and for this reason, a centralized system, which means that if you want to join tables one with another, if you want to move money for sure, you must have a control of the whole database. So this must be centralized. Centralized in computer science terms means on, let's say, a single machine, on a machine you control, okay? This sets the limitations of the solutions of relational databases, which are very fine, very efficient in doing this until you move them on a distributed situation, on a distributed cluster, okay? And by the way, what happened in the last, let's say 20 years, 10, 20 years, is that everything is moving, every service is moving to a distributed solution. Okay? Why? Because basically 20 years ago, let's say roughly, I would say the web economy, the digital world, the user-generated content emerged. Okay? And so previously, we had few connected people, few connected items, few connected things to the internet, less user-generated contents, less digital services. Okay. Instead, in the last 20 years, specifically the beginning of the new millennium, let's say, many companies like Google, Amazon, Facebook emerged, okay, providing digital services to the whole population of the world, okay? And these set the expectation for a new service and for a new type of data management behind the service, okay? So here is the goal. So we are moving from an entity relationship design, which is executed ex ante, I would say. So when you design databases in relational world, some of you have done that. You use the entity relationship modeling typically, and you sit down, you analyze specifications, and you design based on the specifications, your entities and your relationships. And that holds and give the shape to the whole database. Okay, you end up creating the tables and populating data. Instead, in a rapidly evolving situation, so imagine you're a startup, I would say 20 years ago when there was the boom, but even nowadays, okay? You're in a startup, you design your database, and then you iterate fast, collecting feedback from the market, from your customers, from early adopters, and continuously improving your service, okay? You end up changing your database every day for adding features, removing attributes, adding tables, and everything, okay? And this is driven by your, basically your application. So if you need to present every time courses with students, every time you're doing the join, okay? And this is heavy, computationally heavy. Instead, the idea of NoSQL is if you always aggregate the courses and the students, why don't you put them together? Okay? If you need to aggregate the students with the exams and the grades, why don't you put them together? Okay? So it's driven by your need at application level. The need of the application level is to have an aggregation of data available at once, okay? Then the front end doesn't care about how the back end gets that. Being it a join or a pre-aggregate data structure, we will see later, we don't care. Okay, so that's the idea how NoSQL was kind of born, okay? So, yeah, that was the comparison with the classical relational model. We have seen that. So I have the customer here, the order here, the invoice here, the order item here. But when I get an order, okay, when I get an order, I also want all the order items to be there. So I need to do a join here every time I access an order. And sometimes when I get a customer, I also want all his or her orders, okay? So all of these stuff can be connected by relationships saying not only which joins I can do, but which pieces of information are called aggregates. So data that I access together in my application, okay? So that's the idea of NoSQL. Now, what is the value of relational, which we will challenge in a minute? A standard data model, entity relationship, okay? Mature technologies, because they were born in the 70s, so it's 50 years of technology. That's a very big plus. Acid properties, atomicity, consistency, isolation, durability, we'll see them one by one, because we will challenge those, okay, with NoSQL. Basically, this is the financial transaction properties, okay? Well, basically, they are very, very mature, okay? Very mature technology, very popular, very successful, okay? They have a fixed schema known a priori. That's a result of your designing and doing introduction databases courses, okay? So the schema is, you know, this one, okay? That's the schema, okay, of a table, okay? Normalized, so no duplication of data. The student name is only in the student table. If you want to get a student name, you do the join and you get the name from the student table. Okay, you don't store the student name outside the student table, never. That's normalization, okay? And the transactions ACID, okay? Now, how do we move from this word to the NoSQL? First, this is fixed, okay? This is fixed as a schema. However, in real life, especially if you're in a startup, it's clear that if you are in a very well-established banking sector doing the same thing since 50 years ago, you don't have this problem. But when you live in a period like the last 20 years of rapidly evolving digital services, okay, you live in a world where you have a rapidly changing need, okay? Your data modeling, your database design would change every day, okay? Then, sometimes you don't know in advance your needs. If you are a startup, you think about what could be useful, but then the market says it's not exactly like this. You need to change a little, sometimes more than a little. And so you rapidly evolve because you actually don't know, you are guessing the expectations, the results, the need of your customers, okay? Then, these solutions here, if you're normalizing, you're storing the name of a student only in the student table. But you are in a big data context, in a distributed system where you're serving millions of customers across the world. You have probably your database distributed in different places around the world. And so if your student table is in Europe, in the Europe database, okay, and you have a customer from Australia, you need to do a join with the data in Europe, which waits for the round trip time and all the stuff. Okay, so it's very inefficient. Okay, it would be better to have a copy of the data in Australia, okay, or to have a different data structure, which doesn't require a join. Okay, also transactions. Transactions require all the participants, all the nodes of your cluster to agree on sending money to someone, okay? All the people must say, yes, let's send the money to that bank account, okay? So distributed transactions are very heavy, okay? We'll see that in details. I'll show you how is the protocol of distributed transactions in relational databases, and we'll see how instead NoSQL will work with that, okay? So in distributed environment, we have some inefficiencies, okay? We are kind of slow. We still work, we as relational databases, but we are kind of slow, okay? So how can we get out of this situation in which we are these emerging digital services, which for the first time are directed to the whole world, okay? So in the last century, there was, I guess, very few services delivered digitally to the whole world, okay? Nowadays, if I am, I don't know, Netflix, and I launch a new series, I can send it all over the world, and I have 1 billion views in one day. I can possibly have 1 billion views in one day, okay? Instead, if last century, but this century as well, I launch a book as a physical level of existence, I cannot have 1 billion readers at day one, okay? Because this means I had to print all the copies in advance, which is crazy, okay? I put it on sales, and then while they are buying the book, I will print it, and this means days, deliveries, and all the stuff in real life. Okay, so digital services have this essence of being volatile in some sense. So you can deliver a service digitally immediately to billions of customers, okay? Whereas the physical goods have the limitation of the physical space to be created, to be sent, to be set up, all this stuff, okay? So that's the idea. So how was NoSQL born? Actually, the oldest term NoSQL you can find on Google is from 1998, okay? That's a fake news in the sense that we are not interested into that specific database whose purpose was only having no SQL interface, okay? That was something we are not interested into. Instead, we refer for the first time to NoSQL as a hashtag, which is in 2009, okay? They were organizing an event to promote this new class of databases, okay? They were already kind of increasing in popularity, so they were born at the beginning of the year 2000, okay? The first years, and then over the year 2000, we'll see in a minute. And then they needed a name to group them all, okay? And so they used a short name because they need a hashtag on Twitter, so it must be short, and they use NoSQL, okay? So what is NoSQL? It's a term which is very vague, I would say, so there is no precise definition. It groups a very heterogeneous family of databases, okay? So it's like saying Italian and non-Italian, okay? So even Italians are very different, but we say Italian is kind of group of databases. Then you have non-Italian, but non-Italian means Australian, US, Eskimese, or anything, okay? Japanese or everything, okay? So the outside world is much more heterogeneous, right? That's the same for NoSQL. So the difficult part in teaching also NoSQL is to identify some features in common for all such databases. Okay, it's like defining non-Italian people. How can you define non-Italian people? It's difficult. It's difficult. Okay, so I identified among the many features you can find 3 features which are founding, are core of the NoSQL databases. First, they do not have joins. Second, they do not have a schema, or at least not a rigid schema. And they have a feature of horizontal scalability. What's the strange thing about this slide? That I'm introducing the new iPhone, and the new iPhone has no camera and no, I don't know, you choose what. So for the first time, I'm introducing a new database technology, something new because it was born in the new millennium, a new century, whereas relational databases are the previous iPhone, last century, okay? So that's the new iPhone. I'm launching the new technology, and new technology has less features than the previous one. What's wrong? There's something wrong here. So we need to understand why we have this situation here. And the why is very simple. No join. We said that join are the most expensive operation in relational databases, okay? If you are born in a very highly competitive market like the new century first years, and you compete with Google, Amazon, Apple, and all on Facebook and all the likes, okay? You don't have time to do expensive, computationally expensive operations. You must be very quick. So what happens in race cars? Race cars do not have air conditioning, okay? Because air conditioning has a weight, And if you want a race car to go fast, you don't have the weight, okay? So you remove the A conditioning from the race car to go faster. We remove the join from the new iPhone, from the new database, to go faster, okay? So that's the reason why. Schema. Why do we remove the schema? Because it's a rapidly evolving situation. We are launching for the first time in the world new digital services to serve the whole humanity, okay? That never happened before. And so my service is evolving every hour, okay? So I cannot actually design a database because it's all by the time I put in production, okay? And so that's the reason why I have a solution which has no rigid schema. It allows me to be flexible in my data storage so that I can adapt to any change on the fly, okay? So these are the main reasons why you see no camera in the new iPhone, no schema in the new iPhone, okay? And we'll see next lecture why horizontal scalability. Okay, so time is over. Thank you very much and see you next time.